What's the basis of a vector space? So a set of linearly independent vectors is the basis of a vector. Do they have the vectors in the basis have to be orthogonal to one another?
No.
Because in two space, that forms the basis of a vector space. Also, those two form the basis of a vector space. So as long as they're linear, those two vectors that are close to one another, they are still linearly independent of one another, although they're not orthogonal. What do we call the basis in which the vectors are independent of one another? Well, they have to be independent, but they're orthogonal to one another and they have unit length. What do we call that basis?
OrthoNormal.
The orthonormal basis is the one with vectors that are orthogonal to one another and of unit length. What is a norm? What's a norm?
A norm has to do with measurement of a vector. I have the notes pulled up right here, so I can tell you exactly what you said it is.
Okay.
The length of a norm or of a vector x is defined as double bar around x is equal to the summation of xi squared, square root of that.
So it's just like you did in 8th or 9th grade, you had to measure the distance between 2 points in the Euclidean plane. And so you put the difference in the x's and squared it, the difference in the y, and squared it, you add it together, and put the square root that told you the distance between 2 points in the plane. So same here. Besides that Euclidean norm, are there any other measures of distance that one might use?
The T norm is similar to the Euclidean norm, but we use T as a
Perfect. And you may have heard them referred to as LP norms. So that the Euclidean norm is a special case. The absolute distance, so the absolute difference between x1 and x2 and y1 and plus absolute difference between y1 and y2, if you have 2 points in the plane, that would be another LP norm, a very special one. And
I didn't hear you said linear section.
no, he said, I asked, are there any other norms besides the Euclidean norm, which we got from Mike? Right, we got that. LP. P is, L is for length, and P is for the power that you use in, so what you learned from Miss Crabtree in 8th grade was the following. There's so the distance from A to B, Miss Crabtree told you was x1 minus x2 squared plus y1 minus y2 squared. That's what Crabtree told you. Why couldn't we use as our measure of distance? Because squaring the difference between the numbers makes the difference quite big. So if they're very far apart, squaring it makes it a big number. Why couldn't we use, for example, the cube root of x1 minus x2 to the third power plus y1 minus y2 to the third power? That's another one. So P is the power to which we're raising things. And as it happens, absolute difference is a special LP norm. And in fact, if you stick with me through next semester, we'll spend a lot of time talking about LP norms based on absolute value, because we'll talk about something called quantile regression. These squares, all the regression analysis that you've talked about so far is all based on Euclidean distance. And in least squares regression analysis, we're minimizing the length of the error vector when we pick the regression coefficients. The difference between the observed dependent variable and our prediction for what it is contingent on our choices of regression coefficients. So we choose those regression coefficients to minimize the Euclidean difference between what we observe and what our best guess is. minimize the sum of absolute deviations. And in ordinary regression analysis, garden variety regression analysis, that work with this class, the loss associated with an error is symmetric. In quantile regression, we could make the loss symmetric by doing median regression instead of mean. Or we could just model the 10th percentile or the 75th percentile, depending on how asymmetric the